Here I have the datasheet from the microcontroller from Texas Instrument. Here I'm going to give you just a quick review of what we were talking about previously. This is the section GPIO, which is General Purpose Input Outputs. Here, if you look at the datasheet, every time you're working with microcontrollers, you have to go and read the datasheet. The datasheet will tell you everything about the architecture of the microcontroller, all the registers, all the inputs and outputs, the peripherals it has available, how to configure them, and the addresses. The most important thing, it will tell you the addresses and what bits and what configurations you have available. In this case, here it tells us the GPIO of this microcontroller has port A, B, C, D, E, F. It has basically six ports available and up to 43 programmable inputs and outputs. This is the characteristics of this microcontroller. We go, for example, GPIO special considerations. Here you can see some special configurations. For example, for each port, it will tell you what is the default state. This is the default state. When you reset, every time you reset the microcontroller, you will get this configuration. For example, if we go over here, here's the diagram. This is the digital I/O pad, and for each of the ports, we have one of these blocks, which has port control, commit control, mode control, and you can basically manipulate all of these registers to configure your GPIO port. Here it gives us more data, how the data register works, and here I want to show you where the address here. It will tell you here, for example, for the port A, what is the address. This is where the port A begins. Port B, port C, and D and F. We are interested in this one, the port F. Now this is where the port begins, but if we go a little bit here, for example, for each port we have the data, we have the direction, and here will tell you basically the offset. That means from this address you just have to add this 400, 404, and if you point to the 404, then you will be pointing to the interrupt sense or interrupt event or interrupt clear, depending on where you are. This is very useful. Here we can change the direction, whether it's input or output. Here we can select the pull up resistor or pull down resistor, depending on what you need. And I just want to show you this because this is very useful when programming microcontrollers. Always come to the data sheet to look at the registers, and we're going to do just that. We're going to configure the registers in order to work with in order to manipulate the ports, the port F, and turn on our LED. In order to configure our GPIO, well, we need to follow these steps. These steps are in the datasheet, so if you read the datasheet, you will find that these are the steps that you need to follow in order to configure the port. You need to enable the clock. This is step number 1, enable the clock by configuring this register, and then you need to set the direction. In this case, we need output. Configure the F cell to program each bit as GPIO, because remember, we can have a GPIO We also have other peripherals such as PWM, ADC, and many other peripherals. So we need to specify, we need this as GPIO, general purpose input output. Then to enable the GPIO, we need to set the then bit in this register GPIO then, and so on. So we're gonna do just that and we'll show you how to do it. Here we are. Let me delete this. Okay, so we'll begin right from scratch. So what I'm going to do is I'm going to paste this here. I have already defined each of the registers. These are the registers that we need: the clock, data, the direction, AFCell, and the digital enable. These are all the registers that we need in order to get started with our Blink application. Here I'm gonna do just a small, as you can see, this naming convention, we're using a _T. I'm just gonna go ahead, modify this. I'm gonna modify the naming convention. This is what we defined previously: 8 bits, 16 bit, 32 bits. In the ARM microcontrollers, each register is 32 bits long. That's exactly what we're saying here. This is a pointer. Please declare a pointer. This is telling us it's a pointer to this address, and it's type volatile with. What this volatile means is basically it's telling the compiler this variable here that we are defining can change at any time, because the compiler has something called optimization. So if the compiler sees that this variable is not being used in the code, it will optimize it away. It will think this is not a variable that you're using. I will optimize it away. Volatile, by using volatile, will telling the compiler, please don't optimize this away, because it is a pointer to that address. So what I'm going to do is I'm going to activate the port F by writing 2. Then I'm going to make port F2 output. That is the blue LED. And then disable the alt function. We don't want the alternate function. We want the GPIO. We have to enable the digital enable for that port. And then disable analog functionality on this port. And here I'm going to introduce you to a loop. The while loop, what basically is telling us is, please execute everything, the code, execute everything inside this loop while this is true. A 1 is always considered true, so this will basically loop and execute indefinitely until we stop our debugger, our application. This will keep running. This is called, and I'm going to put here, this is called endless loop. Why? Because it will always execute, it will always be true. We will always run until we decide to stop the code. And what I'm going to do is I'm going to use this remember this bitwise. This is an XOR. What I'm doing here is doing an XOR on whatever is in the port in the bit 2. We are shifting, remember, we're shifting the 2 bits, and we are doing this XOR over and over again. This causes the bit to be toggling from 1 to 0. This is very one of the very useful operations to toggle a bit in microcontrollers. So let's test this. Okay, so we have errors. Let me see. Okay. Okay, yeah, I see what the problem is. GPIO. Alright, let's build. And now we're gonna step into configure our registers. There you go. And then we enter the endless loop. Toggle the bit. Again, endless loop, toggle the bit again. And this will continue over and over again until we decide to stop. Here we have you can see the board, it is on. If we click, we step into, turns off. Then again, we step into, on, off, on, off, and so on. This will continue endlessly until we decide to stop our program. Explain a little bit more about what is it that we are doing here. You may be wondering why 4 to this address. Let's explore first the direction address and why we are writing a 4 in this address. So let's go back to the datasheet. In the datasheet, we can see here's the direction address. Remember that we have the base address of the port, that is this, plus the offset. We will point to this register, the direction register. So what this datasheet is telling us is we have 8 bits available to configure our port, and each of these bits represent one input or output that we have available. So depending on, if we write 0 here, for example, we are saying this is an input. The output 0 is an input. If we write 1, we're saying it's an output. Depending on what we write. So what do we need to write? You may be wondering. Well, to know that, you need to go back to the schematic. Here in the schematic, you see that port F bit 2, this is the one that is connected to the blue LED, which is the one that we are targeting. So bit 2 of the port F. Let's see how we can set the port 2 of this register by converting from hexadecimal to byte. Here we have our converter. If we convert this to binary, you will see that we have 8 bits, 8 digits. First digit is 0, second digit is 0, and the third digit is 1. So third digit is 1. which basically would be, this is 0. We start counting from 0. This is 0, 1, and 2. So bit 2 of the port F is being set to 1. Here in the datasheet, we start from 0, 1, 2. This bit 2 of the port F is being set as an output, which is exactly what we want, right? Bit 2, port F, bit 2 has to be an output in order to be able to control the blue LED. And that is exactly what we're doing here. And we're doing the same thing. In this address, we're telling it, by doing this, we are disabling the alternate function. By doing this, we are enabling the digital function. And by writing 0 here, we are disabling the analog functionality. And by doing this, this is exactly the same thing. Remember that we're shifting, by doing this, we're shifting the 2 bits to the left. Well, if we shift 2 bits to the left, this is the same as basically doing this operation. Let's try that. Let's try, instead of doing shift, let's try this. I'm going to peel. I could do the shift, or I could explicitly tell it I want bit number 2. Please do an XOR operation on that bit, and let's see what we get. Yep, we get exactly the same behavior. We're toggling our LED, because we're telling it, please toggle bit number 2. Do an XOR operation over and over again, and that, as a result, that bit toggles from 0 to 1, from 1 to 0, and so on.